Hello, I'm Tom Lucas and I work at the Purdue Polytechnic Institute. I'm a professor in engineering technology, and today I want to talk about automation and the future of work. Before we can dive into that topic, it's worthwhile to think about what work are we talking about? What is work, especially in the scope of production? So to start off, I want you to look at this image and consider, what is this? Um, you may recognize the wooden handle looking side and a hole on the top. That's actually for putting grain. This is a manually spun hand milled grain machine that grinds your grain for you between the rocks. So that is the work that's being performed in the scope of production. Humans are directly providing the energy through that handle. And the machine, as simplistic as it is, being a set of grinding rocks, are assisting by actually producing the grinding, converting that human energy into the grinding motion that's producing the milled grain. We have a similar setup here. The production and the output is actually almost identical within that little house shown in the image. But the energy is no longer being provided by a person. It's being provided by that spinning water wheel and by the flow down the river, as shown in the picture, that spins the wheel. And then within that house is grinding the grain through a couple mechanical connections. So you have that same output, but now the energy is not directly from a person, but it has been designed by a person to utilize some energy from nature, from that flowing water. Again, we have an upgrade to the similar system. The work being performed is to grind our grain, but that energy is now coming from an electrical source, which may ultimately come from a steam-based or burning-based power factory. That means you're no longer reliant on if there was enough rainfall to power that river. In theory, we always or almost always have access to our electrical source or our steam-based source. Machines are assisting in the grinding. They're now more robust, more powerful, and involve molded metal parts, for example. But we still have the same product being produced. As we advance again, we see a larger scale of this same work being performed. We now have a factory line setting. Machines are assisting with the grinding. They're driven electrically at every stage. But now you have production lines in parallel that are producing the same output, but across a larger spread. So your overall quantity of output is much larger as long as you coordinate the incoming grain, for example, to make sure it's distributed appropriately. So there's more managerial aspects to this production line, but the output, again, is an upscaling of grinding the grain, or acting as a mill. And with these four elements, the very first human grinding the rocks was off the left of this scale, but each of the stages that we just walked through represent part of industrial evolution over time. The very first element being off the left side of this chart, but what's considered by scholars in this area as the first industrial revolution happened when we started harnessing water and steam-powered factories or manufacturing facilities. In the second industrial revolution, we introduced the assembly line and infrastructure that used electricity and gas, so you had more reliable systems. You had things like telegraph and roads that allow you to communicate longer distances. In the third industrial revolution, we had the introduction of electronics that allowed us to make informed decisions in the production, so we could look at larger sets of data through techniques in lean manufacturing, for example, and you can have control of systems through PLCs and computers. This allowed you to have more dynamic manufacturing settings, and it allowed you to look at your outputs and your quality and your efficiency at much larger scales. Where we are today, or where we're stepping into today as a society, is known as the fourth industrial revolution, or Industry 4.0. And we have a lot of new technologies that facilitate that. So we can communicate incredible distances around the world mobily without any physical wired connection. We can have centralized data storage accessible at all times and from all locations. With cyber physical systems that can adapt to information and make perhaps new and more complex choices on the fly, so allowing the customers to have access to customization that was never before possible, and access to a service that may not have been in their control previously. So there's a lot to unpack here. This figure covers mainly the technological element, so the question is, where are the humans in all of this? They were mentioned as our energy sources previously, and they still play a critical role. We, the humans, still play a critical role. So there is a lot you can dive into within this topic. And for our talk overall today, we're going to zoom into a couple of key elements. But overall, our themes will be, at present, unskilled human labor is being replaced with robotics more quickly than at any time in history. And in countries that are economically equipped to handle these changes, they are occurring at a rapid pace, and new human workforce interaction concepts are being developed. And so the overall question we hope to address is, what will the human workforce look like in the future? We're going to separate that overall scope into three small sections. First, we'll look at the robotic applications of today. Then we'll go through the robotics being developed and rolled out perhaps in the next few decades. And then, so that'll be under the robots of tomorrow. And then we want to explore, what is the human factor in this? How do humans influence the design, the programming, and the execution of these cyber robotic systems? And what does their role, or our role, in the workforce look like going into the future? So let's start off with a look at the robots of today. So machines were developed to assist with dangerous and difficult jobs. That is often the overarching driving force behind a lot of robotics. And robotic workers are used in a number of different areas, not just manufacturing, but have seeped into all facets of human social life. So we want to define what is a robot and why we use robots. We'll highlight some applications across a broad range of industries, then talk about what types of skills are required to interact with robots in their current state, and then how is their design influenced by how they will be used. And this helps us inform later on how humans will interact with robotic systems. So the idea of a robot is a very old concept. It's been around for a very long time. There are early examples as far back as 270 BC. A robotic, broadly considered robotic element could have been a clock. And depending how far you're willing to dig, there are other, even earlier examples that you could potentially consider a robot. And the reason you can consider it a robot is, under a broad definition, a robot is simply a machine or device that operates automatically or by remote control. And what's not said on the slide is generally to aid in some human task. Most robots, especially these days, are designed to assist with tasks that would be dirty, dangerous, or dull, things that humans are not wanting to do. So things like carrying heavy loads, repetitive tasks, tasks that need to be happening at very high speeds, maybe beyond what's comfortable for a human. Tasks that perform a lot of computations or require a high amount of computations with good accuracy, and then activities that may just be unsafe for humans in general. And you can see in the plot here the development and really rollout of robots in industrial spaces has nearly tripled in the last 10 years. From 1 million rollouts 10 years ago to a workforce of 3 million robots, and that's just continuing to rise as we move forward into the future. So a few examples of why we would use robots are are going to be shown now. A dangerous environment is a classic situation where you maybe don't want a human user doing something like carrying out a bomb disposal or collecting data from an active volcano, exploring hazardous environments. And we'll focus on a few of those in just a moment. But also for military operations where you don't want a human in an at-risk location or state. Or maybe for a dangerous rescue. If a human went somewhere that is dangerous, you don't want to send more humans in, but you can use robotics in many cases to aid in rescue without endangering more people. Within manufacturing logistics, so think your Amazon warehouses and UPS distribution facilities. Robotic elements are used for moving packages around and handling heavy materials and pallets. Pick-and-place robots can move products from conveyors and package them at extremely high speeds, much higher than a human user could in many cases. And robots are very useful in food processing, where you need to have a completely germ-free, clean environment where the human element, as it relates to bacteria and cleanliness, is not acceptable in that particular state. Robotics can be used in clean environments. So, of course, robotics has made its way into our homes as well. We have many smart devices in our computers, refrigerators, blenders, watches. All of these devices are moving towards communicating with one another or communicating more advanced information. Refrigerators that track your shopping lists or can maybe track the expiration date of something are not too far off. So, tying back to hazardous environments, space exploration has always been a classic case for robotics, as NASA is constantly developing and producing robots for space maintenance, such as on the International Space Station, or for exploration of other planets. There have been a number of highly publicized areas where this has happened. But even within our own terrestrial environment, we have the underwater exploration element that robotics are great for. The high pressures at deep sea locations are obviously not suitable for people, and robotics give us a way to capture information from these unexplored locations. Within the medical realm, it's not only about the robustness of robotics that we see in a lot of the exploration or dangerous settings, but robotics offer a level of precision that is not always easy to replicate from a human user. Even a very skilled surgeon maybe has a day where they're not quite as precise they were on a previous day, and that may or may not make a difference in a particular situation, but the idea of robotics in medical environments allows you to work on procedures with the highest possible precision that can be mechanically designed. And then in laboratories, you can transport biological samples or chemical samples between instruments without a human, who would be maybe dangerously exposed, involved at all. And then within the realm of prosthetics, robotics has some obvious applications there in mimicking human elements or appendages, for example. So we have all those different examples of robotics and their applications that are out in the world today, and you can probably go and find many of those things at your local department store that do many of the tasks we saw above. Not all of them, especially the danger or medical, tend to be more specialized, but to create robots that do things that we want them to do, there are a few elements that we can consider that will inform how human users design these systems and interact with these systems. So how can we get the robot to do the task we want? There are some design choices mechanically in the mobility that we create for it and for its manipulation style, which could be a hand, it could be a gripper or a suction cup. But robots are not limited to the type of manipulation interface that we have as people, which is a hand. So we also have the logic or the brains behind the robotic system, which is typically interfaced through some sort of computer programming. is the interface of how you design the logic of the computer. How does it think? How does the robot think? And then how does it perceive the world around is done through typically through what's referred to as a sensor, which is just an element that's able to capture some physical quantity and convert it into an electrical quantity that can then integrate with the programming, and the robot can use a combination of programming and sensed quantities to make decisions of, am I welding this car frame on the left side or the right side, for example, based on which way the car is oriented in front of the robot. So you need mechanical design, and then you need logical design as well. So the mobility can be a lot of things, and it's very application specific. As people and as animals, we envision legs on things, 2 legs, 4 legs, maybe more. But types of robotic locomotion can be extremely dependent on what the application is. So are they fixed in place? That may be appropriate for a factory line setting, or do they move mobily on wheels, on legs, maybe through jumping or hopping or sliding? There are many mechanical mechanisms you could come up with for how a robot moves, and it's incredibly application dependent. And then that's the robot itself moving, but then how does it interact with the world around it mechanically? Any kind of feature you could think is probably could apply in some situation, from finger-like appendages to more foreign things like scoops or suction cups, or pressure sensing probes. Interacting with fingers is how we visualize things naturally, but when you're kind of separate the human element from that in designing a robot system, there are many different types of interfacing for manipulation that might be appropriate. And a lot of times for us as people, those historically have taken the role of tools like a shovel or a rake or fork or spoon. So in designing the thought behind the robot, if you will, how it makes its decisions on how to move or what to do, computer software is usually involved at this point. Historically, software has been fairly simple and straightforward. If you encounter this condition, do this, and more dynamic forms of control have evolved over time. Systems today can adjust themselves based on how their manufacturing process is going, and it's envisioned in the future even more intelligent adjustment or dynamic adjustment could be possible through different advances in artificial intelligence. And the information that informs this intelligence comes from sensors, which again are just capturing environmental elements such as temperature or wind speed or viscosity of a fluid, and sending those to your computer system to make decisions based off of those elements. Sensors are already distributed all over the place. If you have a phone in your pocket right now, there are many sensors on that phone to determine which side of the screen is pointed up, or do you have the screen turned sideways? Are you shaking the screen around? Are you looking at the front of it? There are tons of different sensors, even just in a phone or in a modern automobile, that inform how that system works. And so that information, combined with forms of artificial intelligence, are what can give you robotic a sense of intelligence, although it's not the same as human intelligence. So we do want to think about, being that we're at this current state of already fairly advanced robotics where we can have a robot mimic a task, what comes next? And so advancements in the machines we've been talking about are moving technology closer and closer to lights out manufacturing, or the idea that there will be no human operator and the need for human elements such as having the lights on. But laborers, and rightly so perhaps, are fearful of how these changes affect their employment, and what will their role in this type of situation be. And so in turn, how will our future economy be impacted? So we want to dive into Industry 4.0 specifically. We walked up to the modern day in some of towards the beginning of this presentation. Now we want to look specifically at what's going on now that will inform the next decades. So we want to look at the giant leaps that signal to us that we're reaching Industry 4.0, Revolution 4.0. And then look at examples and impact areas, how those changes ripple out from just the manufacturing or production level areas and how they impact other areas in society. So with Industrial Revolutions Phase 1, 2, and 3, we ushered in mechanical production, railways and the steam engine, and then mass production based on electricity and assembly lines to do a lot of processes in parallel. We then introduced computers, which gave us huge access to computation and data collection and repetitive tasks. Distributed over the internet, for example, was towards the end of that. But how we look at the hallmarks of our next industrial revolution, if you think back to 2006, all of these technologies listed here that are very commonplace today did not exist. Even the iPhone just came out a year later after I strategically chose this date. But all of these things did not exist. And so the advances between even the last 2 decades have been incredible. And if you look back in time, some very impactful technology shown here, and this plot shows the number of years it took for each product to gain 50 million users. You can see airlines took 68 years to reach 50 million users. If you zoom forward towards computers, even still took 14 years before they reached that amount of people. Keep moving forward, internet, only 7 years. And then YouTube and Facebook, 3 and 4 years. And the last example on the plot is Pokemon Go, which is an app, game, and it took 19 days to reach 50 million people. And that's one of the hallmarks of what Industry 4.0 is grounded on, is this immediate distribution and access to data. If you look at a lot of these elements, the ones that took longer were typically related to a lot of physical infrastructure. How do you get people onto an airplane, move it from an airport that you had to build on an airplane that you had to build to an airport that you had to build on the other end. Televisions, ATM, even computers required building, but as you move forward, you're incorporating more and more instant access data and instant access to distribution. So for example, iPod, you now have to have a physical iPod, but what's on it is instantly or quickly available information, and so it's extremely customizable. YouTube, purely a data endeavor, as well as Facebook and Twitter, and Pokemon Go as well. And so as we convert the goods that are desirable towards more digital assets, along with or coupled with faster internet speeds, we're able to distribute things incredibly quickly, and some of those impacts will reverberate back to physical manufacturing of new things. And so what's now possible because of our digital data infrastructure is the idea of a cyber-physical system, which means you have some physical plant collaborating with computational elements in real time. Systems that are engineered to have operations that are monitored, coordinated, and controlled by some computing and communication core. And they allow us to add abilities to physical systems by providing a virtual infrastructure. And what I mean by that is, if you think about a distributed production of something like a car, you may have different pieces built in different states. But in the vision of Industry 4.0, you have the whole picture of your virtual factory process being worked through in a digital format, in a server somewhere, that is coordinating on-the-ground sensors at different physical locations. So if you have an error or a part break at one place, production speed could adjust in another location. And you have coordinated activity across different physical distances in near real time. And this can offer a lot of advantages, such as input reduction. You're not wasting parts because you can speed up or slow down or alter production based on what's going on at other plants. So you don't make too much or too little of a part. And ultimately, This mass coordination finds efficiency, which typically shows itself in business as a cost reduction. So that is the dream of Industry 4.0. So the integration of automation, big data, cloud computing, autonomous elements in decision making, along with interconnected devices, IoT or Internet of Things, and complex data management. Combination of all these is what the hallmarks are of Industry 4.0. And there are huge potential impacts across many different disciplines. In agriculture, for example, it is commonplace currently to, if you want to pesticide a field, apply it to the whole field or water a whole field equally. But if you had sensors monitoring which locations needed more or less water, you could more efficiently use your water, avoid overwatering, or target applications of fertilizers or insecticides to avoid just getting in your plane and spraying the entire field and hoping for the best when it may only have been required at one certain location. Again, you need advanced robotics and sensing infrastructure to do that, but research is actively underway to make those things possible. Within manufacturing quality, you now have larger and larger data sets across different physical locations. And the idea of collecting all this data in the cloud, if you will, or a centralized data location, coupled with artificial intelligence, offers the dream of having more efficient systems overall, just by seeing a very large picture of the whole manufacturing process. In terms of supply chain, you can monitor incoming ingredients and outputs in real time to adjust manufacturing, adjust where things are being shipped or sent, or even ordered from. So you have a good equal distribution. You're not ordering waste or producing waste at points within your supply chain, or running into bottlenecks that are interrupting the flow of products. Within retail, you can begin to not only capture consumer information, but you can produce consumer products through things like additive manufacturing, which can give you customized products on the spot through things like 3D printing, to give the consumer a more customizable experience. Or the idea of augmented reality. You may have seen in some department store apps, you can go to the item and hit an augmented reality button to see what, for example, a side table would look sitting in your living room. Some of the apps have integrated that, so you can already see some applications of augmented reality today. Within healthcare, analyzing large amounts of data can help healthcare providers make better decisions, help even governmental officials make better decisions on how money is allocated and resources are allocated. Within pharmacy, you can, again, look at data, increase quality and productivity of different drugs that are being introduced, or find ways to have cost reduction and avoid waste by looking at large data sets. In energy, energy historically is really a top-down process where energy is produced at a plant and distributed to neighborhoods. But with mass data collection, you could have opportunities for people to have energy exchanges if they've outfitted their house or their family with something like an electric car, which would have a battery for storage, or maybe have solar panels on their house. So they could have some different exchange or storage options with the power grid if there is a much higher level of data integration. And so the impacts are everywhere. There are examples in play. Another example from a specific company is the German company Siemens, an industrial user, uses Industry 4.0 in their medical engineering. It used to take a long time for artificial knee and hip joints. It took several days to customize them, and now new 3D printing and manufacturing techniques have allowed you to create a custom part for a patient within 3 to 4 hours. So you could have what was previously a many-day process or multiple doctor's visits happening in one afternoon. And another example, another German supplier makes laser systems that keep track of what they have produced throughout the day. And if adjustments need to be made, it could slow down production or lower its laser power if that's an application here. to give it a longer life cycle if it doesn't need to produce at maximum speed all the time. And this gives you efficiencies in terms of extending the lifetime of your manufacturing elements, as well as making sure your supply chain is all coordinated with itself. You don't produce extra parts or are lacking extra parts. So the impacts across the economy in general will be huge, just in terms of economic growth and the scale of companies, the way that companies age their products. You've seen a lot of products turn towards updates rather than being retired and a new product being introduced. And that's available because of the digital formats. You'll see the scale for productivity changing, and really even the definition of what productivity is has some flexibility depending on the type of product. And all these impact the humans involved in the economy in terms of their employment, what they are and aren't doing, so labor substitution, and the nature of the work itself. So businesses will have a role in deciding what are the customer expectations, what does data show about products, how can they collaborate with others to meet these needs, and what kind of operating models need to shift. So a lot of historically top-down style systems where you have one central point distributing to a lot of smaller elements may need to be inverted, where you have data collection from smaller elements informing overall larger systems. And the scope of these changes is going to impact every scale, from national and global governments to society and peoples at large. There will have to be concern on the equality of the distribution of these technologies. What people are we having work, and in what type of situations? How does this impact communities when these type of systems are implemented, in terms of what it does to the populace, what kind of work they're doing, what hours are they doing, what's the effect on the environment around it. And then the individual, us as people, have an identity and morality and ethics that come into play and are stressed when we're put in a position of what is my purpose in this huge system. And so there's a human connection that needs to be considered. And as you saw in much of what we just covered, the human factor is not always what's publicized as you drive forward these technological advancements. And so our last section today is going to talk about what the human role is and recommendations for considerations moving into the future. So what will the human workforce of the future look like? What type of training and education will be relevant? And just what does the future hold in this area? And so we're going to look at the current state of what industry looks for in people moving into Industry 4.0, and then look at some human elements that need to be considered as these industries come to maturity. And so we'll start off with just a future-ready skill set for this rapidly evolving technology. One thing you notice as you look through this list is it's not specifically working with a type of technology or with a specific manufacturing element or a technical ability. It's about an openness to learn about upcoming technologies, work with others, and be creative. You have software turnover more and more quickly these days, and so you're not guaranteed that what you're doing today is what you will be doing tomorrow. And so being able to adapt is highly, highly valued moving into this rapidly moving technological space. Competencies for these type of areas typically are at the intersection of humans, machines, and data. So machine learning and Internet of Things interact with how machines and data work together. Cybersecurity and threat intelligence is at the interface of data and humans, both good and bad actors in that space. And then automation and robotics is the interaction between your humans and machines. How does the work get completed? And careers in these type of areas follow the same trend, where the human-machine interface has some future-ready careers, and there are at the human and data interface you have security-related elements. At the machine data interface you have 3D printing solutions and different types of manufacturing engineers. So this interaction between robots and people and the data that informs their choices is where a lot of this new approach to industry is going to take place. And so humans are at the core of all of this. The future of human workers, the manufacturing environment will impact the workers, and the workers will then impact performance. And so it's really a decision process and a design process of what do we want to trust robots to do and what do we want to trust humans to do, and then looking at how they interact when we form a big picture of what the future of the worker looks like. And just to zoom into those two elements, worker health and performance, ergonomics in general is just being concerned with the interaction with humans and the other elements of the system to optimize human well-being. This is not always a high priority as new manufacturing technologies are put into place. And you can see estimated workplace mortality is fairly large. And population studies indicate that a lot of human workers are inflicted with musculoskeletal disorders from repetitive work, injury tasks. In some sectors where they're literally performing the repeated task as their whole job, those rates can go up to 100%. And so one question that comes to mind as we think about worker health is, are we having humans perform the jobs that they are best suited for? And we need to very consciously decide as we move forward as a population what the future of industry looks like. And it can't just be robots are the entire emphasis and then humans just fit in to fill any gaps, because we can see there are issues with health of the human operators. And when you have health or ergonomics issues, that impacts performance. Humans are required for certain elements where computers are not appropriate. And so studies looking at human outcomes on systems find that there are advantages to keeping your workers safe and healthy and in good emotional states. But quantitatively, these benefits are not always a single data point. It's buried within larger financial scopes. And so they're difficult to isolate. And that makes it difficult for managers and engineers to design and make decisions based on this. And so how does what people recognize to be true compare to what we can measure? You may know a factory of well taken care of workers produces better results, but how can we actually capture that? And so moving forward with the idea of industrial design, these Industry 4.0 factories don't currently exist on a broad scale. And so the last thing I wanted to wrap up with was ideas of key concepts for future industrial designs. So for one, it's important to consider that these 4.0 systems are socio-technical systems, meaning they have both humans and machines interacting with each other. If there's a mismatch between the capabilities of a worker and the demands of the system, you're going to have negative consequences within the space. And so intentional attention to these details of the interaction of human and machines is critical. And attention to the human factor must occur throughout the entire process design. It's difficult to fix an issue after a production setup is already in place. So if you have a human doing a task they're not suited for, you can add a cushion on their seat or an air conditioning, but it's not going to fix your core problem. And those are not necessarily specific examples, but just in general, I'm saying improve the comfort of that space, but it doesn't improve the overall system. You need to have intentional design in the setup of your robotic integration, not just bring in a new robotic arm and hope the human can adapt. Human system interactions work best when they engage more than just repetitive mindless tasks. Humans operate best when they have some sort of interaction, perception-based element where they can look at something or see a change they need to make and then have some motor action that is relevant to addressing that change. So that means giving the human an active role in what they're doing. You can see in some settings robotics take over a lot of the work and the human just fills in a place where the robot can't do one particular thing, but that can lead to high stress environments. And employees experience mental strain when working in conditions that have high demands but a low sense of control. It's been shown for decades that employees have high strain under those situations. And finally, because you have such large-scale organizations planned for this future Industry 4.0 situation, complex organizations with many moving parts tend to drift to unsafe states, meaning the minor elements or small subsections of the system try to optimize themselves and minimize costs where they can. But when you have many different small units making small optimizations and minimizing costs, you can overall bring a system to an unsafe or unstable state where injuries may occur, for example. And so in the implementation of the future of manufacturing, a top-down approach to just safety and what it means to have a stable and safe and human interacting system, there needs to be some regulation or forethought in what that means. So the big picture is, to date, a lot of the Industry 4.0 research, the future of the robotic workforce, have broadly ignored humans for a lot of it. The tech pushes forward, by companies and by universities, and there is some look at the human worker element, but the implementation has not been broadly studied. But it needs to be as we move into implementing more of these type of distributed industrial settings. So there are no engineered systems without humans. It's critical that we do this. Humans cannot be re-engineered, and so systems must accommodate the characteristics that we have, or potentially be prone to failure in some way. Not necessarily the process will fail, but your employees may not match the duties being given to them, and that can have other social impacts if they choose not to work, for example. So in general, robotics and the idea of that has been around forever. Not forever, but for a very long time. Aristotle, for example, made the famous quote, "If every tool, when ordered or even of its own accord, could do the work that befits it, then there would be no need for either of apprentices for the master workers or slaves for the lords." So this idea that you could have a non-human element doing your work for you has been around for a very long time. And we've progressed very much to the point where we can have robotics do a lot of sophisticated activities in our daily lives. And contrary to dystopian-minded media, these improved robots are not going to replace workers. They still require some sort of human interaction to either do tasks that we don't have the mechanics to be able to do, or to provide creativity and thought that we don't have the computer infrastructure software-wise to do. Industries rise and fall, but these are all opportunities. So just because the good jobs of the past don't look like the good jobs of the future, not necessarily a reason to despair, but we have opportunities for employment and education for the betterment of all. And so you may see fewer human workers, maybe welding or doing heavy lifting, but there is absolutely human need for skill at the top end of creating the Industry 4.0 type of systems we discussed. And so with that, I'll leave that for you to think about. Thank you for listening.